queries in chat box. Queries will be cleared by the end of today's meet. All the participants are supposed to keep their mics and videos off. At the end of today's meet, we will be taking a photo with our speaker, so please turn on your videos at that time. Now, going ahead with our session, I am Suhani Sawant, the Vice Chairperson of RAS Student Chapter. RAS, what exactly it is? RAS consists on enlarging automation and robotics knowledge by organizing workshop and expert talks. RAS trains students in various aspects of robotics. IEEE DBIT RAS Student Chapter presents Motor and Automation, an expert talk on motors used for industrial automation. It's a great pleasure for me to introduce our today's speaker, Mr. Yogesh Gholap, research scholar at IIT Bombay. Mr. Yogesh Gholap received BE degree in electrical engineering from Vivekanand Education Society's Institute of Technology, Mumbai, Maharashtra in 2009. Further, he completed a degree in electrical engineering in Indian Institute of Technology, Bombay in 2016. He is currently pursuing PhD in electrical engineering from IIT Bombay. He is currently working on security in cyber physical system as Prime Minister's Research Fellow awardee. He has worked as an execution and commissioning engineering in Siemens India Ltd. He has teaching experience in PLC network commissioning. He has teaching experience of over 10 years as assistant professor in Don Bosco Institute of Technology, University of Mumbai, where he had been faculty advisor for IEEE RS and in charge of robotic clubs and School of Automation. His research interests include embedded designs, electronic instrumentation, signal processing, robotics, mechatronics, industrial automation, IoT, and cybersecurity. So, everyone, please join me in welcoming Mr. Yogesh Gholap. Thank you.
Thank you. Yeah, so I think I should share my screen. Am I audible first of all?
Yes, sir.
Okay, okay. So I will share my screen. Okay. Please let me know once my screen is visible.
Yes,
Yes, sir, it's really good.
Okay, great. Okay, so good morning, and I think we'll start without any ado. Yeah, so okay, fine. Yeah, so there are little bit quite a few softwares I'm working on here. So let me know if in between something goes wrong. I request Frida ma'am, if in between my connection goes, please call me. Otherwise, I will keep talking and I will not come to know what is happening. Okay.
Sure, sir. Sure.
Hi, yeah. Thank you so much, ma'am. Yeah, it happens quite a few times in online lecture that I don't come to know whether I'm disconnected or not. Okay, fine. So let's start. Okay, so I will keep things more of the demonstration oriented over here. So I have a couple of videos and couple of simulations over here, which we are going to see. And my today's talk will be based on, as we have seen, different type of motors basically in automation field. So what are the motors? Okay, motors are basically devices which convert a electrical energy, right, to a mechanical energy. And there are two different type of electrical energies which we have that are alternating current and direct current, AC or DC. So basically, if I look at different sources of energies which are available in general, right? They can be categorized as a thermal energy. That is, we have thermal electric power, we have hydraulics, we have wind, we have nuclear. What is happening? Low resource may affect audio. Okay. Anyway. So wind energy, nuclear energy, electrical, solar, all of these are okay, various sources of energy. And we are concentrating on particular source, which is a electrical energy, right? So if I talk about various actuators also, okay, basically actuators are nothing but the output devices in the automation system. And in case of many of the systems which we might see, we will see that these actuators are either a pneumatic, that is based upon the okay, compressed air, hydraulic will be compressed liquid, electric are the motors, right? And a magnetic energy that can be used. Okay, so there are also electromagnetic actuators available, like relays or solenoid valves, which you might have heard. Okay. So if I look at the application area, okay, of these devices, I think many of you might have seen some of these devices, right? So definitely our motors will be there in the electrical vehicles. Okay, they can be seen into the industrial manipulators. Manipulators are the robotic arms. Okay. You definitely have seen this particular device, right? This is our a lathe machine, so you will be having a rotation motion over there. You might have seen okay, in various industrial scenarios, the motors have been heavily used. Okay. So this is the example of the paper mill where okay, the rolls of the sheet paper sheets have been okay, very carefully manufactured, and they need to be very accurately rolled over that pin at very high speed. Okay. So basically, our electrical motor gives us a rotational motion. Okay, actuation is in type of a rotational motion, but these actuation can also be converted to the a linear motion, right? So uh, it is possible to do this with certain mechanism. I hope some of you might have definitely heard about this two type of uh, joints in the various designs. Basically, we have a rotary joint, also called as a revolute joint, very often written as R type joint. And there is a prismatic joint or a linear joint, okay, sometimes written as a P or a translational motion, right? So translation motion is something like this, a linear motion, okay, which is possible like that. And if I have a rotary motion will be around particular axis. So this is particular RRP means what? It is rotary, rotary joint and the prismatic or the linear joint. So all these joints are possible with the help of the electrical motor. There are Cartesian systems, there are cylindrical, there are SCADA that are the okay, robotic arms, which okay very heavily used in various automation fields. Yeah, a moment of uh, uh, if you have any questions, any doubt, please stop me there and there itself. Maybe moderators can pitch in. Yeah. So let me know if you have any question. You can definitely ask in between. I will also stop for the, uh, time to time. So let me know if there is any uh, confusion in between later on when we talk about some okay, hardware also or programming. Please stop me. If you have any small doubt, okay, no issue. Okay, definitely will try to answer those questions. Okay, so I was talking about the linear motion. So linear motion is possible with the help of the motor. So there are certain mechanisms. You might have seen this particular mechanism, okay, which is a ball and spring mechanism, which converts a rotary motion into a linear motion. So okay, basically there is a motor at the end and there is a lead screw going on. Okay, and as the motor moves, this okay the payload on that lead screw can be moved forward and reverse if motor rotates in anti-clockwise or clockwise direction. Right? There is some question of what? Okay. Yeah. So very often, you'll find this type of converters available over there, and this is one of the classic example of a linear motion, a rotary to linear motion. Okay, so there are stepper motors which are used, and these are the pick and place robot or the machine. Okay, the device over here, the vehicular devices are the links are called as the linear actuators, okay, which have been controlled using a stepper motors, or sometimes in a heavy load situation, they can also be a servo motors. Okay. So this is a Cartesian type of robot. So with the help of a simple motors which produce a rotary motion, all three axes, okay, there is a X, Y, and Z axis. Three axes are there, right? All three axes, linear motion is possible with the help of the mechanism we have just seen. Okay. So not only for rotary, I want to emphasize here this motors are also used for the linear actuation. Okay. So in today's talk, we'll be discussing about various DC motors in primary, but let us quickly look at some of the major type of the motors. So as I mentioned, the motors have been divided into two categories: AC motors and DC motors. Okay. AC motors are further divided into two parts called as the induction motors or asynchronous motor and the synchronous motor. And induction motors, synchronous motors are further divided into a single phase, three-phase motor, where basically our stator has a rotating magnetic field, and the rotor is going to catch up along with that particular field. In case of a DC motor, we are going to have two types like brushed DC motors and brushless DC motor. And brushed DC motors will be again divided into various motors like permanent magnet motor, a compound shunt type motor, series type motor. If I look at the application point of view, the AC motors definitely give us very high torque. Okay. So whenever there is a requirement, like say your electrical trains, okay, definitely you have electrical cars, all of them will be having the AC type of motors very often, and which generates a huge torque. But the problem with them is the speed control and the accurate position or the speed control will be a little bit difficult in case of the AC motors. These are done with the help of certain drives called as differential speed drives, okay, variable frequency drives basically. So VFDs are used, which are more expensive and difficult way to control the speed. On other hand, if I look at the DC motor gives us a lower torque. Okay, so in simple applications like say robotic arm and all, we'll find DC motors where the accuracy of motion, okay, or the speed of moving from one location to another matters. The way we have seen in one of this Kara robot, where I need to be exactly moved. This particular arm need to be exactly moved by say 1 centimeter, 2 centimeter, or whatever, wherever you sense the presence of the your object. So in such cases where very accurate control are needed, we often go for a DC kind of environment or DC motors, okay, which are easier to control. So if I look at the induction motors, okay, maybe in details, the detail you can find that the induction motors have a slip ring, squirrel cage, or synchronous motors. But today's talk, I will try to concentrate more about the DC motors. Okay. So in case of DC motor, what we are going to look at today in nutshell. So I will give you a quick overview. There are going to be four motors which we will discuss. So along with the some of the programs with the help of say a Arduino controller. I'm going to explain these motors. These four motors are a simple DC motor, a stepper motor, a servo motor, and brushless DC motor or BLDC motor. We'll talk about how to interface these motors. So to interface these motors, we require something called as a motor drivers. So for DC motor, I can use simple relay or I will require a power transistors. For a stepper motor, okay, we require power transistors or a driver called as ULN 2003 or TB. Okay, these are the name of various drivers. Servo motors, again, okay, you require power transistors are possible, or you can use modular drivers. Brushless motors are more expensive and they require specialized speed controllers called as ESCs or electronic speed controllers. Subsequently, we'll look at the two more most important part when we talk about the interfacing the motor, how to control the direction of the motor and the speed of the motor, and how torque of the motor is related to this. Okay. So if I talk about a simple DC motor, the direction of the DC motor, simple DC motor can be just changed by swapping its terminals or by swapping the direction of voltage or a current flowing through the terminal of motor. Speed can be controlled by changing the voltage, okay, with the help of a technique called as a pulse width modulation. Okay. So PWM here stands for pulse width modulation. And yeah, even though it sounds a scary term, we'll definitely try to okay, simplify it and understand basically what is the application of it. If I look at the stepper motor, the direction of the stepper motor can be changed with the help of something called as the changing the actuation sequence in the coil, and the speed of the stepper motors can be changed by changing the square wave, basically which controls the step size of the stepper motor. Subsequently, in case of a servo motor, again, the direction here will be changed with the help of this technique called as a PWM. And later on, for the BLDC, okay, the speed is changed with the help of the PWM. So the bottom line here is something, this word which is getting repeated, PWM, very important. Okay, so we'll discuss this in a little bit more detail when we'll discuss various videos. Okay, so I'm trying to. This is the target of today's talk. Okay, so there will be four motors which we are going to discuss with various examples, the programming and the simulation example. A DC motor, a stepper motor, a servo motor, and a BLDC motor. Okay. So let us begin with the basic simple DC motor. So simple DC motor can be constructed with the help of a permanent magnet and a coil like that, and the motoring action can be uh, produced with such kind of effect. So you might have tried this kind of small actuation of a or generating the rotary motion with a simple coil like this, maybe in your physics courses during your junior college or something. Maybe in 12th you might have a similar topic. So, or you can try it out. This is quite a fun exercise, right? So, if you get a time, there are good videos on YouTube. You just require a battery, a good copper wire, and a single magnet, using which you can create your own uh, DC motor over there. Right? So, a simple motoring action, that is the current carrying conductor is going to force, going to experience a force if that conductor is placed in a magnetic field, right? And based upon the direction of the force, the particular coil is going to be rotated over there. So a DC motor, like that, basically has a two terminals. It is going to have two electrical terminals, and these terminals you can supply them with a DC source or DC voltage, and by changing the direction of the current through this particular motor, I can change the direction of the rotation, as simple as that. So if I want to change the direction of a DC motor, I need to swap the battery potential. And if I need to change the speed of this DC motor, basically I need to increase or decrease the voltage of that particular device, okay, that particular motor. So speed control is done with the help of the voltage, and direction control is by simply swapping the terminal. And these are some of the popular DC motors which you will definitely find, and you'll be requiring these motors later on, okay, when you go for your maybe final project or so. Okay. So if I look at a speed control of a DC motor can be done with the help of controlling the voltage or current, and basically voltage is directly proportional to the current. We have this famous Ohm's law, right? V is equal to IR. So by increasing the voltage, you can increase the speed, or by increasing the voltage, you can basically increase the current in the DC motor, and which will also increase the speed. Another thing is, if I increase the torque, if I want to increase the torque of the motor, also your torque is directly proportional to the current. So more the current, higher will be the torque. Or other way around, if your shaft is given a higher load to be moved, right? So if the load in particular vehicle, particular system increases, then motor is going to draw higher current from your power supply, and that need to be sensed and limited very carefully. So if you design a system which is supposed to work at say 5 amperes, then there will be say particular torque that will be coming along with that current, right? So you cannot load the motor beyond that torque. If you try to load the motor beyond the torque, one problem might be that your internal coils are going to be damaged, or the lead wires are going to be burnt out. Right? So definitely we need to be very careful while designing the system out there. So let us look at these two things. As I mentioned, uh, with all these different motors, we are going to concentrate upon the direction control and the speed control. Okay, how to control the direction of that motor or the speed of the motor. So I will take some basic examples of a simple Arduino programming. So I hope some of you have heard about this device called as Arduino. Have you heard about the Arduino? Anyone? Are you aware of this particular device? Yes, please. Yes.
Sir,
Yeah. Yes.
sir, actually we have disabled their mic.
Oh, okay.
They are putting in their chats. They have heard, sir.
Oh, okay. Okay. If right. So yeah, I think maybe in your mini projects and all, you may definitely require this kind of a controlling device. So a little bit about the Arduino. Arduino is a embedded platform. It has a microcontroller called as Atmega 328P, which have been manufactured, designed by a Atmel Incorporation. Right now, it has been procured by Microchip Incorporation. Yeah. So this particular device, or Arduino, has 18, roughly 13 digital input outputs which can be used to control various devices. Yeah. So we'll try some simple program to, let us say, first control the direction of the DC motor. So let us not go to the controller. Let us first look at a simple switch-based control. Yeah. So I'm having a simple SPDT switch. Okay, so what do I mean by SPDT? Okay, so we have a single pole double throw kind of switch. Okay, SPDT switch. Okay, single pole double throw switch where, okay, so this is the symbol of the SPDT switch. There is a single pole and there are two throws. Throw is the place where our device will get, our armature is going to connect the pole. So there is a pole and there are two throws for that. And the changeover from, okay, the connection between this pole and throw 1 and 2 is made with the help of the armature. And this changeover is done with the help of a mechanical person need to push that button, right? So that a pole can connect from throw 1 to throw 2. Okay, simple button, basically electrical switch. So if I want to control, say, this particular motor, I have a DC battery over here. Okay. So currently, if switch is at the bottom position, what is happening? The negative terminal of this battery, the smaller terminal is a negative. It is getting connected to the, okay, say, first end of the motor, and second end of the motor is going to be connected to positive. On the other hand, if this particular armature is at the top position, then the battery B1 will provide the, okay, voltage in other direction. So let me try to simulate and let us see what happens, right? So currently, I hope you can see that current is flowing in particular direction, right? Where a B2 is getting connected, okay? B2 is active and motor is rotating in the particular direction. I hope you can, okay, see this motor rotating there, right? And please notice now a changeover in the direction once I switch the position of the switch, right? So as soon as I have moved the position of the switch from a throw 1 to throw 2, the second battery got connected, which is B1, and the motor is rotating in other way around, right? Okay, so that is the simple trick how we can control the direction of the motor. Okay, usually, okay, there will be two wires coming out of the DC motor, and if I connect them to a different polarity of the battery, where direction of the motor is going to be changed. As simple as that. Right? So if I want to, okay, change the direction, but here it is saying that I require two batteries, right, to change the direction and single switch, which is quite absurd, right? I will not keep on having multiple batteries and, okay, uh, trying this out. The more easier ways, usually you are going to have a single power source, and using that we need to control this particular device. And this is done with the help of another type of switch called as DP-DT switch, dual pole, dual throw switch. Okay. So in this particular case, we need to, okay, perform some, okay, electrical connection. I hope in the current connection, what is happening? The top wire of this motor is getting connected to positive of the battery. The lower wire of the motor is getting connected to the negative of the battery, right? So if I want to change the direction in case of a DP-DT, there are two poles. Okay, so if I talk about a DP-DT switch, okay, this is a DP-DT switch. We have two poles, dual poles. Okay. DP stands for dual pole, dual throw. There are two poles and there are two throws. Okay, six lines are there basically here. So when I change this particular armature position, pole 1 and pole 2 are going to swap their position. Initially, pole 1 was connected to this throw 1, throw 2 over there. Okay, if I move this armature down, okay, at the same time, this pole 1 will be connected over here, and here pole 2 will get connected over here. So if I want to perform the connection over here, I can do a simple trick. Currently, okay, pole one. Okay, if I move this down, what should happen? Okay, in up position, this is how the throws are going to be changed. When you press the switch over here, when you push this button down, what happens? The internal mechanism is going to change the connection, electrical connections from a particular pole to different pole. So here in the when this armature is at the top position, positive is connected to the upper side of the battery and negative is the bottom, and it will basically reverse the connections, right? So what I can do is I can okay, go something like this, right? So here in the bottom position now, if our armature is at the bottom position, then the negative of the battery is coming to the top, right? And the positive of the battery is going down. Okay. If I keep this at the top, what is happening? Positive of the battery is going to the top. So if I simulate this by changing, please notice the changeover of this motor. If I change this particular switch, what happens? I hope you can see this, that direction of the current and the potential has changed, right? So motor is rotating in other way down. Okay. So basically, direction control here can be achieved with the help of a single switch and single power supply. Very often, you'll find this kind of arrangement in uh, uh, mechanical based. This is basically a mechanical switch, right? So mechanical control of the direction control of the motor. Very simplistic control without any programming involved over here, right? So maybe some of you might have gone to those robotic competitions, right? These robot wars and all where you are controlling the motor through some remote control, and there will be a joystick, right? Or multi-direction switch. So very basic joystick can be made with the help of two DPDT switches, and you can move the motors in the forward and reverse direction to control those motors. Okay? So this kept apart, if I want to do this now electronically, okay? Instead of a mechanical switch, if I want to use electronic control, that means if I want to do this with the help of a microcontroller, then what to do, right? So in that case, would require a device called as a relay. Okay? So the diagram I'm keeping same here, right? What is happening? In place of a mechanical changeover, that is by manually moving this particular armature at a top and bottom position, this change should be done with the help of a electrical or electronic signal. This is done with the help of a relay. So relay has another agent. Okay, you can see the symbol. The upper part is this armature. Now I cannot control this manually. Okay? I cannot push it down with a mechanical force. For that, we use an electromagnet. So this is the symbol of electromagnet or coil. And this coil can be used to push or pull this particular armature. And this entire device is called as a relay. It is an electromechanical device. Okay? So a relay is very often used in the electronic control of mechanical uh, devices. So this is a simple relay, right? Here you can see that relay has a coil. So this is your solenoid or a coil, which is wound around a soft iron core. And if I energize the coil, what happens? The armature is basically the small soft iron bar, which is going to be okay push from towards the switch or away from the switch. So this was a simple DP. This is the SPDT switch. Yeah. If I look at the animation, right? So if I energize the coil, what happens? This armature is going to move the particular switch from, or the central position can be thought to be a pole. It can be moved from, say, throw 1 to throw 2. The same way, okay, which we have seen in our earlier example, right? So this is now a electrical or electronic control of a mechanical action. Mechanical action is what? A pushing of the switch, okay, from throw 1 to throw 2, switch or the pole. And this is done with the help of electrical power over there, not electromagnetic power, right? So this is a simple relay which can be utilized over here. Some terminologies, we have a coil over here. This coil can be energized, it can be controlled now. So this coil have been given something called as a logic supply or a control supply. Usually logic 1 means turning on the coil, and logic 0 means turning off the coils. Logic 1 is, in terms of voltage, is very often say 5 volt, and logic 0 can be a 0 volt. Okay. Again, here I'm assuming that coil rating is a 5 volt. Okay. So if your coil rating is a 5 volt, then by applying a 5 volt, this coil is going to get, okay, magnetized, which will, okay, push that iron bar towards one side, and the connection can be made. And other way around, if I, okay, turn off the coil, or if I don't apply any potential, this will go to its, the normal or default position, right? So there will be again a spring action in this device. Okay. So with the help of such device, we can, okay, control the motion of this, or direction of the potential. And this can be shown over here, that the same action now of changing over the switch, we are trying with the help of a relay, and relay is getting controlled via the a microcontroller. So microcontroller here is Arduino. I am connecting one of the pin of this Arduino, right? This is the D1 or digital pin number 1. I'm connecting it to the coil of our relay, and by making this digital pin high or low, we can energize or de-energize the coil, based upon which this changeover will happen. So let us quickly look at the simulation. Okay. So currently, after every couple of seconds, okay, I'm turning on and off the pin number 1 of the microcontroller, and which is basically controlling the motion or the direction of this armature, right? So changeover is taking place after every 2 seconds, because of which the direction of motor is also getting changed. Okay, and the reason why motor direction is changing is because, okay, our battery terminals are swapped because of this arrangement. Okay. I hope we are following till here, right? So let me stop for the question. If anyone have any doubt or question till now.
Prem, are there any questions posted? Students, please post your queries in the chat. Post will read out the questions.
Let me see. I can wait for a minute if anyone have any doubt, query, because these are very important part, and if you understand this, definitely we can move ahead. Okay. So the software which I'm using is called as a Proteus, and can be installed. You can get a student license, evaluation license for 30 days, and you can try it out. This is very handy software while designing and simulating various electronic devices. So along with the Proteus, I need to get, there is something in the chat. Is it, how much is approximate delay that is given? Yeah, that is it. Alden, yeah, I hope. Yeah, so the delay is 2 seconds over here. Yeah. So let us look at the program, and this will become more clear in that case. Okay. So let us look at the Arduino code, and very simple code. Don't be afraid of it. It is simple 4 or 5 lines as seen on our screen here, right? So in Arduino, we have a setup and a loop part. In setup, I need to tell that which pin, okay, I'm using to control our relay, and that pin is used whether as an output pin or an input pin. Okay. So currently, I am configuring pin number 1 as an output pin in a loop which gets executed infinitely. That is, you start executing this code line by line. Whenever your Arduino code starts, you search, or your compiler search for a setup function. It enters inside the setup function, execute whatever is there inside the setup function, and after setup function is executed, it goes to a loop function. Okay, then loop function will start executing line by line. Okay, once loop function comes at the end of it, that means this bracket, it will again reiterate this process from the first line of the loop function. Okay, so loop function, the name loop is because it keeps executing the same stuff inside that function again and again. So setup function executes only once in its lifetime, okay, which is used to configure various IO direction of your, okay, controller. After setup function is exited, you will enter inside the loop, and now you cannot come out of the loop, okay, unless and until your controller is powered on or, okay, restarted, basically. Yeah. So what is happening inside a loop function is the first parameter here is again a pin number. So pin number 1 is kept high. It is then waiting for a certain amount of time. This is done with the help of a delay function. It takes a parameter in a millisecond. So here, if I write delay of 1, then this function will stop for 1 millisecond. That means your digital pin 1 will be kept high for 1 millisecond. So if I want to keep that digital pin high for say 2 seconds, then I have to provide the value as a 2000, right? So 2000 millisecond means 2 seconds. So after making that pin high for high, we are going to wait, or your Arduino is going to wait for 2000 milliseconds or 2 seconds. After that, we are going to make that pin low. Same pin is made low, or logic 0 is applied on pin number 1, and we are waiting again for 2 seconds, right? And this is happening in an infinite loop. And this entire code you can basically create with the help of, and compile that code, creates a hex code, or the your machine code for that particular program. And this machine code can be loaded in the simulator. Okay, so the simulator has a facility to load the machine code, which is generated by the Arduino in form of the hex file. So I have bound this with this simple interface, and the same code is basically used to change over the direction of the motor over here. So this changeover is happening after every 2 seconds. I hope, okay, I have clarified the question, right? So let us move ahead. So the problem over here, uh, that's why I have kept the second diagram here. This is the transistorized drive. Okay. We have seen in my introduction to the motors that we are going to talk about the drive, or how to control the motor. Very often, okay, if you try to use a direct relay or induct, this relay basically has a coil, or it has an inductor. Coil is nothing but an inductor. To directly connect such coil to the pin of your microcontroller, what happens? This inductor basically can draw a huge current, right? In case, let us assume that, okay, something wrong is happening in this particular circuit. This is a power circuit, right, which is connected to your, okay, actuator. If something goes wrong, motor gets stuck or anything, say your wire gets shorted over there, the direct effect will come on your expensive microcontroller pin, right? They, either your digital pin D1 will get damaged, or it is also possible that entire microcontroller will get burnt. So to safeguard our microcontroller, eh, we use this particular device driver. One of the use of our driver. Okay, this is now a transistorized driver. I'm using one of the NPN transistor to drive the particular relay. Okay. So it is going to isolate the output load from your input load. So transistor base resistance, if you remember, is very high, base emitter or the base collector basically, and base emitter is very low. So basically it's kind of isolate. Secondly, this transistor is nothing but an amplifier, right? You might have heard this during your basic course. Right? So transistor performs two actions. It boosts the current which is coming from your controller, and now you can turn on and off this particular relay with a sufficient power. Okay, if you directly connect, it may get turned on and off. Okay, in a physical scenario, if you take the physical relay over here, it may not get actuated itself because your controllers do not provide enough current to actuate this kind of load. So we need a amplifier, a current amplifier. The name are different. The same thing is called as amplifier, a switch, or a driver. So all three names are used over here. In this case, this transistor Q1 is acting as an amplifier. It is also acting as a switch, and it is also acting as a driver. All three names are synonymous in this particular case. Yeah. So whenever I provide a logic 1 to the base of this transistor, so your transistor will turn on, which is going to make this particular coil energized, and the further actuation will take place. So same circuit, okay, but this is what is often done in your controller, in your DC motor control. You'll never directly connect the relays to your microcontroller. You will always pass it via the drivers. So simplistic driver is a transistorized drive, okay, with the single NPN transistor, and subsequently we'll see a more better configuration of these drivers. Yeah. So same thing is happening here also. We are applying the logic. I'm taking the same pin out. Your digital pin 1 is connected to the this particular driver, right? And this transistor is getting turned on and off after every 2 seconds, okay, based upon our program. So yeah, whenever you please keep this in mind, whenever you use later on in your curriculum or your application, you need to use a driver along with your actuators. Okay? Electronic driver are very essential. To first thing is to boost the current or the voltage and or voltages at the output circuit, and the second use of the driver is you are going to isolate your controlling device from the actuation device. So whatever bad happens, that bad will happen with this driver, not the expensive controller. Okay, you can easily replace this transistor, okay, but it will be definitely very costly to get a new, comparatively costly to get the new controller. Yeah. So I hope, yeah. Is there any question? Let me just check once. Where is that? Yeah, any question till now? I'm not able to go. Yeah. Okay, I think I answered the previous question. Okay, great. So I hope we can move ahead. Fine. So we have seen relay-based drive. We have seen the transistorized drive. let us go to little bit better control. Okay. So yeah, one more thing I want to talk about is in case of a transistor, we also need one more kind of protection that is called as a back EMF protection. Whenever there is an inductive load like this, we know that the inductive loads or inductors will be okay, generating or going to induce the electric energy inside them whenever there is a varying current through them. Current is changing through inductor. It is going to create a or it is going to induce a EMF called as a back EMF. And to safeguard our device from this back EMF, we use certain mechanism. This is called as a freewheeling diode. This diode is utilized, okay, which is basically safeguards our transistor here from a high speed fluctuations. So very often the transistorized drive we find such kind of diodes along with them. Okay, so we know the Faraday's law, right? Faraday's law says what? The induced EMF, if current is changed, then uh, in an inductor, then your EMF is going to be induced, and that is directly proportional to the rate of change of current, di by dt, uh, by multiplying it with the inductance. And let's just say that the voltage, which is, I'm sorry, voltage which is generated will have the exactly opposite opposite direction with the applied voltage, right? So basically here, if you look at the applied voltage is going like this. It is this particular terminal. Okay, we are connecting to our, this is my positive terminal. Let us say 5 volt, which is connected like this, plus it is going to a negative direction like this, right? So whenever there is a current, this will be the direction of current, right? So because of this particular direction of the current, if the current through this particular device changes, so when this current changes, we know that, let us assume that this particular current is say 1 ampere or 1 milliampere. Okay, let's assume very small current. Okay, so if I turn on the current, okay, there will be a one turn on the transistor, there will be 1 milliampere current, and if I turn it off, there will not be any current, right? So this switching is happening here, right? And this device is keeping that particular magnetic energy. So this magnetic energy need to be released, and this particular current, if it changes, right, there will be change of current. If I switch it off, when the transistor was on, there was 1 milliampere current was flowing. When transistor is off, there will be 0 milliampere of current was flowing. And let us assume this changeover happens within 1 second, right? So dt is 1 second and di is 1 milli, right? And let us assume the inductance is also 1 Henry, okay, just for the sake of argument. So here the back EMF is going to be how much? It will be 1 into 10 to the power minus 3 volt. Okay. So this entire game is based upon this dt. Okay, if I very slowly change the this particular switch, right, after every 1 second, we are not going to get a huge back EMF. But imagine the application where you need to change this particular device at very high rate. Let us assume that rate to be 1 microsecond, right? So if it is 1 microsecond, in that case, denominator there will be 1 into 10 to the power minus 6, right? So this is going to be how much? This entire result will be 1 into 10 to the power 3, which indicates the back EMF can go as high as 1000 volt. Okay, if I switch the circuit at 1 microsecond rate, right? So the 1000 volt is definitely scary voltage and which can damage this entire circuit. And the direction of this 1000 volt will be always the opposite of the applied correct? Right? So this direction of a back EMF will be plus minus like this, right? The direction of the current was like this. By lenses, it says the back EMF will be other way around. And how this diode safeguards whatever is the back EMF, that back EMF is going to be make this diode what forward bias, right? So this diode only respond to the back EMF, not the applied EMF. This blue one is the EB or the back EMF, which is going to okay, flow through this diode, which is going to basically pass that magnetic energy through this diode. And this diode rating is chosen such that okay, it can handle that much current. And this energy is allowed to circulate within this particular loop. And that's why it is called as a freewheeling diode. Okay. So very important. Okay, whenever later on you guys might be are going to definitely use this okay, electropneumatic or electromagnetic experiments later on where you'll be requiring the relays. So keep this thing in mind that always in the electronic control of those relays, we require some protection. And very often I have seen that if people don't use this protection, you will find that your drivers or your controllers are getting damaged, and that will cause definitely loss of, yeah, you will definitely pay on that, right? So again, this is very important from the control part of, yeah. So yeah, let us is there any question on this? Yeah, quickly let me see. Fine, so let us move ahead. Yeah, so that is the importance of the uh, drive circuit and the protection of that particular circuit. Okay. So uh, the circuit seems very complex, right? So if I want a bidirectional control, basically what we do is we go for a H-bridge drive like this. This is called as H-bridge drive, and all the protection which we have talked about, okay, are implemented in this H-bridge drive, and this comes into a package or an integrated circuit called as L293D. So this is the motor driver available, okay, and using which we can basically control a different motors. It can be this driver can be connected to the a drive voltage, so which can be connected to say a 12 volt. If you have 12-volt motor, you require to apply a 12-volt supply to it. You need to apply a logic supply, okay, which is okay, used to control your coil. Okay, so usually drivers are two supplies, a logic supply and a drive supply. Drive is for output and logic is for the input. The same some question. What are the most common method for controlling the speed and direction of motor in the automation system? Okay. Yeah, so as I mentioned, the uh, direction are with the help of the switches. Switches are nothing but transistors, as we have seen, right? And the speed is with the help of a method called as a PWM, which I'm going to describe shortly. Okay. So in case of a DC scenario, these are the things. In case of AC, we are going to look at there are another methods called as the VFD, variable frequency drives. But yeah, in DC, speed control is very often with the help of a pulse width modulation, PWM, and direction is with the help of the switches, the way we have seen. Switches, electronic switches are nothing but the transistors, right? So power transistors are used to control the direction. And yeah, let us quickly look at this driver, and I will talk about the PWM subsequently. Okay. Fine. Let us go ahead. So I was talking about this driver L293D. Okay. So what this driver has? This driver has a input pins. Okay. This input can come from your logic that is your microcontroller, and corresponding input can be amplified and given to the a motor. So this has a internal drive. Okay, so pin 1 is input 1 can be connected to the corresponding terminal output 1. So if I apply say 5 volt, which is my say logic supply, the corresponding 5 volt will get converted to the 12 volt by this driver, amplified to 12 volt. The other terminal of this motor can be connected to say pin, can be controlled using this pin 5. Okay, let us say if I apply logic 0 to this, what happens? This 5 volt. Okay, if I amplify 0, it will still remain 0, right? So another end will get 0 and motor will be okay moving in particular direction. If I want to change the direction, okay, of this motor now, what can be done is instead of 5 and 0, I can apply now 0 volt over here and 5 volt over here. Okay. So exactly opposite stuff will happen. 5 volt will get converted to say a 12 volt, amplified to 12 volt, and 0 will remain 0. So we will get some other direction. So direction control can be achieved over here. Bidirectional control of the motor can be done by applying a appropriate logic value, okay, to this particular controlling pins. Yeah. And let us look at the simulation of this so it might be more clear. So yeah, this is again the internal view is like this. So we apply logic 1 to one side and 0 to another side, right? So logic 1 is going to turn on this motor in particular direction. And if I apply logic 1 to other side, 0 to one side, it is going to rotate the motor in the other direction, right? So this is what is happening internally. That is your logic supplies 0 and 1 are getting converted to a 12 volt or the drive supply. Okay. This is again a simplified view. This also has incorporates all the diodes, freewheeling diodes, which we have talked about. And there is definitely a back EMF protection in this drive. So quite sophisticated drives, but yeah, not that difficult to understand. It's pretty much there, pretty easy to implement, right? So let us look at how to use this drive. So this is a basic L293D drive. This driver, yeah, as I mentioned, can be thought internally. It basically has 4 switches. The switches are nothing. The 4 transistors are nothing but a switches, right? So if I want to turn on the motor in particular direction, I need to apply the battery power to one end of the motor and the ground to another end, right? So this switch 1 and switch 4, when they are close, motor rotates in one direction, and other way around, I need to close switch 3 and switch 2, then you will get exactly opposite supply and motor will be rotating in other direction. So as I mentioned, the direction control is nothing but the switches, and switches are implemented electronically with the help of the transistors. Yeah? So this is just a logic level diagram, what is happening inside the driver, and this driver is implemented electronically with the help of a integrated circuit or IC called as L293D, which has the input 1, input 2, and corresponding output 1 and output 2 is connected to the motor. Okay. So let us look at the program for this. So what I'm doing, I'm connecting input 1 to digital pin 1, D1, and input 2 to digital pin 2. Corresponding output are connected to the motor, right? So the program for this, yeah. So I need 2 pins, pin 1 and pin 2, both have been configured as an output in our setup. And now if I want to control the direction, I need to perform 2 things, right? Pin 1 should be made high. At the same time, pin 2 should be made low. And then we'll wait for some delay of 2 seconds. If you want to change the direction of this motor, then this pin potential should be swapped, right? Pin 1 should be made low and 2 is made high, and then we are waiting for 2 more seconds. Yeah. So this same code I have loaded over here. So in this case, the driver L293 driver is used to swap the direction of the loop. So program is again quite straightforward, right? We need to swap the logic on these pins. I hope you can see this, right? This red color indicates, in case of simulation, red is logic 1 and blue, I hope these colors are visible, right? Blue is logic 0. So our Arduino controller is changing the potential or the logic on these pins, pin 1 and 2, as per the program which we have written. Okay? And based upon that, our driver is taking care of supplying appropriate potential to this motor, right? So logic levels are 5 volt and drive supply here is a 12 volt. Okay, so if motor rating is 12 volt, so our drive voltage also have kept as 12 volt. Okay. So this kind of amplifier, this driver is nothing but is amplifying current, it is amplifying voltage, and it is also protecting our controller from getting damaged, right? So specification of this controller or this driver L293 is it can drive the output device up to 36 volt, and your motor, that means your motor can be rated as high as 36 volt, and the motor which can take per phase current of around 600 milliampere, that is around half an ampere, can be connected over here. Okay, so that is these are the specification of driver, right? L293 driver. Okay. So okay, if you want to drive a 36 volt motor, then simply you need to connect a 36 volt drive supply over here. Whatever is your drive motor requirement, supply requirement, same potential should be applied to your drive supply. Okay. So that is how a simple DC motor direction can be controlled, and in most of the robotic applications which you may be using, this is one of the recommended driver. So it is available on Amazon or whatever site you want. Okay, for some 300 or 400 rupees, you will get them. And okay, you definitely need them to actuate your motors, maybe relays or solenoid valves like that. So let me check for any questions out there. Uh, there is something. I have observed that even though the delay was 2 seconds, but the logic switching take place in more than 2 seconds while simulating. Yeah, absolutely correct. So uh, a very nice observation. That is one of the drawback of the simulator. So the simulators are near real time, not the real time simulator. Yeah. So the simulation, the program which is written for say 1 second, in simulator it might simulate it for a certain duration. So this is the simulation time going on here. It depends upon at the bottom, if you see, it is showing my CPU load. Okay, so currently my CPU is at 58%. If my CPU is busy with something, right, so it will definitely hamper my simulation time also. Yeah. So if I have a good configuration, that totally depends upon the my laptop's configuration. Yeah. So if you have better RAM and better processor, it might be able to simulate in real time. Correct. You are absolutely correct. Yeah. So that is the drawback of the simulator. But yeah, in physical, I hope I'm still connected, right? Yeah. I hope I have answered the question. Yeah. The question was, I think, asking I observed even. Yeah. So yeah, simulators are just for verifying your logic, okay, and verifying the program. The timing simulations may or may not be accurate. Yeah, absolutely correct. Yeah, but it will give us a notion that yeah, your program is working correctly. If your program works correctly on the simulator, then there is a good chance that it will work in real world too, right? In simulator, you just have to okay, do the connections over here. You can have any number of such L29 3D okay, drives. You don't require any okay, hardware for that, no wires, nothing, no messed up business, right? Just do the logical connections and check your code. Okay, and yeah, then you can hope that that code have good chance of okay, working. There will be a 99% in small case you will get very accurate results. But yeah, in very complex programs where maybe you are simulating entire robotic system, you need to be more cautious while designing your delays and okay, great, great, good question. So I think that was it. Yeah, let us move ahead then. Great. Okay. So from speed control, from the direction control, let us come to the next very important point, PWM. Now I will talk about a pulse width modulation or PWM. This kind of control mechanism is used to control the speed of the motor. Same control mechanism will be used to control the speed of a DC motor. Then in case of this mechanism is used, PWM, to control speed of a DC, position in case of a servo, and same PWM mechanism is used in case of a high speed motors or BLDC motors also. It's a very important terminology. So let us look at how this PWM works. So PWM, to look at that, let us first understand how to control a simple speed. As I mentioned before, the speed of the DC motor is directly proportional to the voltage or the current flowing through that motor. Right? So if it is a 12-volt motor, okay, if we are having a 12-volt DC motor, by changing the power supply, okay, if you have a variable power supply from 0 to 12-volt, I can change the speed of this motor. If speed is say 60 RPM, if rated speed of the motor is 60 RPM, in that case, by increasing the voltage from 0 to 12-volt, I can increase the speed of the motor from 0 RPM to 12 RPM. It is exactly linearly proportional. Yeah. So DC motors, that's why are very easy to control. The speed will be linearly proportional to the voltage. If your voltage changes from 0 to 12-volt, then your speed of the motor will change from 0 to 60 RPM if it is say rated for say 60 RPM like that. So quite easy to control and predictably control the speed, which is quite difficult in case of AC motors where we require where speed is directly proportional to the frequency. Okay, so there is something called a synchronous speed NS of a AC motor is directly proportional to the frequency, and controlling frequency okay, of the motor is a difficult task. Yeah, so that's why I said DC motors are often used in a control wherever you have a position or a speed accurate requirement of a position or speed control, we go for a DC kind of setup. So let us look at again a simple example. If I want to control the speed of this motor, what I can do, I can either have a variable power supply or I can use what potentiometer. Very naive or simple approach, right? So you have studied the potentiometer in your 12th class most probably or before that. Yeah? So this is the variable terminal. If a variable terminal is changed from the top to bottom, right? What is happening? The voltage at this variable terminal is changing okay, from 0 to 12-volt. And you can, I think you can observe that the rotation is also going down, right? If I go down, the voltage is going to be proportionally reduced and the speed of this particular rotor is changing, right? It's a very simple way to change the speed. just change the potential applied to the motor from a 0 to the rated value, and you can achieve this particular thing. But the problem over there will be when if this is a manual, this is again a mechanical control, right? If it is a mechanical control, you can buy the potentiometer. Okay, these are the potentiometers are nothing but your you get them as in your in our home we have these knobs, right? Regulator knobs. Those are also kind of the potentiometer, whereby rotating the knob, you are changing the resistance or the potential coming out of that particular knob from 0 to 230 in that case. But okay, very naive approach here can be using this kind of switches, connect the armature on one of end of the motor to the variable terminal of your pot or potentiometer, and you can control it. But what about the microcontroller? Microcontrollers we know are the digital devices, right? Controllers like Arduino and all, I'm sorry, they can only give you output can be either 0 or 1, right? Digital devices. They cannot give you a output varying from 0 to 12 volt. So there is this catch. So to achieve this kind of okay, variable control of the voltage, we are using a certain approach called as pulse width modulation. Okay, so let us talk about what is the PWM. Okay. So PWM is nothing but what we have. We have capability to turn on and off a output pin, right? I can turn on a particular pin or I can turn that particular pin off, right? Only two options are possible. Okay, turn on or off. Either you can get logic 0 or logic 1. What we can control is this delay, right? I can keep this particular pin on for say 1 second, and I can keep this pin off for 1 more second, right? This can be done easily, right? By changing the delay in our program, a square wave of a 50% duty cycle. A duty cycle is the on period divided by total period into 100. So duty cycle D is T on divided by T into 100. If on time is half of the entire period, then you are going to get a 50% duty cycle, which is called a square wave, right? In that case, another approach can be I can turn on the motor for lesser duration and keep it off for higher duration. This is another kind of square wave, another kind of wave that is a rectangular wave now. Okay. Say for 25% of the time, the we keep it on, and the remaining 75% we keep it off, right? So what is the difference here? So if you find the average voltage VAVG, how to find VAVG? Integrate the square wave from 0 to t, okay, V of t, okay, dt, okay, and if you average it over the time, okay, 1 upon t, you will find the average value of this particular. If you solve this integral, find this is going to be, if I consider amplitude to be A or 1 volt, this is going to be 1 by 2. Okay, with 1 by 2 volt, average voltage will be 0.5 volt, or if amplitude is A, it will be A by 2. On the other hand, if I integrate this particular waves, a rectangular wave, you will find that average voltage over here is going to be A by 4, okay, or 0.25. Okay, so the bottom line over here is by changing the width of this pulse, okay, by increasing or reducing the pulse width, what we are achieving, we are able to change the average voltage or effective voltage which is getting applied by this signal. And that effective voltage is nothing but the energy, right? Effective energy is also getting changed. So if I am having a 100% duty cycle, 100% means what? This will never go. This on period will be always there. There will not be any off period basically. Never goes to zero. Okay, it's always on. Okay, so for 100% duty cycle, that is the DC value, you will get V average equal to say 1 volt, or whatever is your amplitude, A volts. If it is 50% duty cycle, we are going to get what? A by 2. If it is 25% duty cycle, we get A by 4 and so on, right? So this is the way to get a voltage or a V average value change from 0 to 100%, right? And using this technique, basically, we can change the effective voltage getting applied to your device. And this technique, that's why it's called as a pulse width modulation. What we are doing, we are modulating or changing the width of the pulse which is getting applied to your motor. Okay. So I hope you understand the problem first. The problem was we cannot directly linearly change the voltage, okay, by with the help of the microcontroller from 0 to 12. What we are doing, we are not changing the amplitude, but the average voltage is getting changed with the help of the pulse width modulation. Okay, if I change my pulse width from 0 to 100%, your average volt will increase from 0 to whatever is your A, right? And this can be then a easier way for a microcontroller to do that. Okay, I hope we are following that, right? Any questions till now? Let me see. Where am I? I guess, yeah. Seems fine. Okay. So I assume that you have understood till here. Okay, so let us move ahead. So this PWM can be done with the help of microcontroller. So microcontroller supports this PWM functionality not on all the pins, but a certain digital pins. Okay. So for example, these pins are pin number 3, 4, pin number 5, 6. From for different controllers, it is different. So you have to look at the data sheet. In Arduino Nano, pin number 3 can be utilized as a PWM pin. Okay, and this PWM pin is going to be connected to now a enable pin of your driver. So this enable pin, what it is doing, it is enabling the output. Okay, the output of this particular drive will be enabled if your PWM input is high, right? So what we are doing here, say pin 2 is connected to one end of the motor, pin number 1 connected to other end of the motor, right? Let us assume that we have applied a 5 and 0 volt to this particular device. Let me draw this here. Yeah. So here we have a driver. Driver is connected to the motor, right? Let us say we have connected this to Arduino, and from Arduino we're applying a 5 volt and 0 to input 1, input 2, because of which this driver will amplify this to 12 volt and 0 volt, so that motor is going to rotate in particular direction, right? So this is now constant 12 volt. But what we are doing, we are using another pin, a PWM pin, where we are going to enable this entire driver, motor driver, whenever this PWM pulse is high. So whenever pulse is high, for this high duration or on duration, your driver is going to be enabled. That means this 12 volt will get applied to this end. And for the enable pulse, low duration of this enable pulse, this driver will be disabled, right? and this 12 volt will not get applied. Okay. So the same waveform, whatever is here on your enable pin, will be observed on your output pin, but at a higher voltage. Right? This might be a 12 volt level, and this can be a 5 volt level. Okay. So your output pin is getting chopped basically. Right? This is also called the chopping, right? At a particular rate or at particular on time, like that. Yeah. So because of which the average voltage at this motor is going to be reduced. If I keep this motor on for say 25% of the duration, then your V average is going to be 1/4 of the supply voltage, that is 12. I'm sorry, what is happening there? Some glitch. Yeah, 12 volt. So 3 volt will be the effective voltage, and okay, corresponding speed will be there. So voltage, this V average will be proportional to the speed of the motor. And by controlling this V average, we are basically controlling the speed of the motor. Okay. So that is in nutshell how a PWM or speed control works. And if I look at the programming part, okay, so how to write a program for that? Program is also quite uh, simple to understand. Now I require 3 pins, right? Pin 1, pin 2, pin 3 is my PWM pin here. Okay, so these are my PWM pin or speed control pin. What pin number 1 and 2 is doing? They are controlling the direction, right? So these are my direction control pins, right? Pin 1 and 2 are direction control, right? So by applying voltage a high or low to this particular pins, we can change the direction. And by changing the PWM pulse width, we can also control the speed of the motor. So there is a function called as analog write. Okay. So in our setup, we are configuring all these 3 pins as output. Inside loop now, please pay attention. What I'm using now new function called as analog write. This analog write function is going to apply a certain value on this pin 3. What value? This analog write function is going to apply a value of variable I. Okay, I hope you remember this for loop from your C language, right? So this variable I is incrementing from 0 till 255 in steps of 50. Okay, I equal to 0, I less than 255. Usually you would have here I plus plus or the incrementation of this variable, right? So I'm increasing this particular value of I from 0 to 255. Why? It is because of the nature of this particular Arduino PWM function or PWM signal. Here, Arduino has a 8-bit PWM. Arduino supports a 8-bit PWM. That means its output, okay, can be changed from 0 to 2 raised to 8. 8-bit is nothing but 2 raised to 8 is 256. Okay, minus 1, which gives you 255. 2 raised to 8 minus 1 is 255. Different possible steps are provided by a PWM of the Arduino, which indicates basically that your output pulse can change from 0 to 100%. Duty cycle basically can be changed from 0% to 100% by changing this PWM value from 0 till 255. So that is how a function is designed. The 8-bit PWM can be increased from 0 to 255 to get a duty cycle increasing from 0 to 100%. Okay, and that is what I'm doing in this function. I'm increasing this PWM. If I want to have a smoother control, I could have written I equal to I plus 1, but for sake of okay, to make you visualize the speed change, okay, I'm giving it a little bit higher value, right? So here speed is going to change in 4 steps roughly, right? And let us see whether we are able to observe the speed change. Yeah. So I will simulate this and we'll see this PWM signal on the oscilloscope connected here. And also I hope you should be able to see the difference. Okay. So please observe that the speed of the motor is increasing. And on the left hand side, I hope you can see the yellow one, the yellow line indicates the PWM signal, where square wave is continuously, okay, the width of the on time of the square wave is continuously changing after every 1 second in steps of 50. Yeah, so we have 4 different speeds of PWM. Okay, here it is say roughly 25%, then 50% speed, 75% speed, then 100% maybe, and then you are going to get a after 100 you'll get a zero speed. Okay. I hope you are able to understand this. Let me see, are there any questions? Yeah, I hope you are with Mitchell here. Okay, fine. So maybe we can. So these are very important concept. Okay, a PWM. If I understood this, okay, in this short time, okay, what we have, it's really a great thing, right? So this is going to be helpful while implementing a lot of different applications in your future work, right? So just by simply by knowing how to control this analog or how to use this analog write function, digital write turning on and off digitally, and with the help of analog write, you can control various aspects of your actuator, the speed as well as the direction. Okay. So yeah, let us move ahead from there. So that was it for the DC motors. Maybe we will quickly go to now a next type of motor, which is a stepper motor. Okay. So DC motor, next type of motor is a stepper motor. So in case of DC motor, we have seen that our rotor rotates by 360-degree continuously, right? But instead of that, if I want a critical position control, right? Okay, very often, we have the requirement that your uh, motor or the shaft of the motor should be rotated by say only 30-degree or 50-degree or say particular angle, okay, and it should come back to some position. Okay, for example, there can be some wiper in your cars, or maybe if you have seen these recording machines, that a spool of the recording machine should be rotated by certain degree to reach to particular position. In case of linear actuator also, you may have to rotate the lead screw by certain number of rotations, so that that lead screw will make that particular position move towards a certain value. So very often the stepper motors are used in this kind of system, where a precise control of a rotation is required. DC motor cannot provide you this kind of this kind of precise control. Yeah? So that is the application of a stepper motor. And again, stepper motors are very simple to understand. Yeah? So stepper motor can have a stator which has coils, and the rotor is a permanent magnet, which is shown over here. What we are doing is, these coils, whenever they are energized, they have been wound around a soft iron bar, and this whenever you energize particular coil, there are 4 coils, or these coils are also called as a poles here. these four coils are energized in a sequence one after another, which generates a magnetic field, which creates a magnetic field in those particular coil. And we know that the opposite poles attract, and accordingly you can see the position of this rotor is changing, right? Here it is happening in a 90-degree. It's also called as a full stepping. So very simple stepper motor can be constructed. Okay, there are two types basically. One is called as a unipolar stepper motor, where there is only single coil, okay, that is energized at a time. On other hand, we also have a bipolar stepper motor where the exactly the mutual diagonally opposite coils are connected together. That means at a time you have to energize two coils. That is the bipolar stepper motor. Okay. So bipolar stepper motor, and in unipolar you have four separate coils where you can connect. Okay, if I apply battery power over here, the coil 1 will get energized, and you are going to get a magnetic field over here, which will attract the rotor, right? And the position of this magnetic field can be changed by changing the actuation sequence. So this is the actuation sequence, quite simple way to control this motor. So coil 1, coil 2, coil 3, coil 4 can be energized in a sequence like that after particular delay. So if I energize the sequence after every 1 second, right? If coil position or coil sequence go from C1 to C2, okay, in a 1 second, then it is going to take roughly how much? 4 seconds to complete one rotation, right? So you can calculate how much can be the RPM. So if I want to increase the speed of this motor, the stepper motor, in that case, we need to reduce this actuation or the changeover delay. If I actuate these coils at a faster rate, in that case, your rotor will rotate at a higher speed and vice versa. Okay. So speed control, in case of a stepper motor, is done with the help of controlling the interstep delay. And how to control the direction of the motor? The direction of the stepper motor can be controlled by changing the sequence. The actuation sequence, if I change, currently it is say C4, C3, C2, C1. Instead of that, if I go for currently it is say C1, C2, C3, C4, right? Instead of that, if I actuate after C1, if I actuate C4, then C3, definitely direction will be changed. So quite simple again to understand how to actuate the stepper motors, right? Speed control is by changing the interstep delay. Direction is by changing the sequence in which coils are getting energized. So maybe we can look at the simulation and the program. So this is the unipolar stepper motor. Okay. Here, by changing, say, the actuation sequence, there are four coils which can be changed. Okay, to move the rotor one after another, I can change the sequence, and okay, rotor can be moved. This is done in a manual way. Rather than this, I can do this in a programmatic way. So to control now a stepper motor, I require four wires, right? If a unipolar stepper motor, there will be four wires for four different coils. And let us look at the program for this motor. So if you look at program, definitely I require four wires for stepper motor. I'm using pin number 3, 4, 2, 3, 4, 5 here. Okay. So these four lines, these four wires, pin number 2, 3, 4, and 5 have been connected to our stepper motor, okay, coils. And how to actuate them? to actuate them, we need to write a appropriate sequence. So coil 1, coil 2, coil 3, and coil 4. Initially, for a 500 millisecond, I'm making coil 1 high. After that, okay, I'm making coil 2 high, right? After pin number, okay, coil number 2 over here is made high. Next coil. Okay. So in a sequence, we are turning on individual coil and waiting for some delay. So this delay is responsible for what? This delay is responsible for, okay, increasing or reducing the speed of our motor. So motor speed in case of a stepper motor is based upon, okay, the delay with which we are, okay, changing this particular sequence. Right? So right now it is roughly 500 milliseconds or 0.5 second. Okay, so it is going to take roughly 2 seconds to complete one rotation. Okay. If I want to move this with a higher speed, okay, in that case, this delay need to be reduced. Okay. So that is the speed control of a stepper motor. And direction will be by changing the actuation sequence. I hope you are with me, right? Any questions till now? Let me see. Okay. There are also the hybrid stepper motors where we can get, so these are the commercial stepper motors. First two types are just for the demonstration purpose, but in, okay, market you'll get the hybrid stepper motors. So hybrid stepper motors are almost similar, but your rotors have more poles or more magnetic positions like this, and based on that, again, sequence actuation sequence can be same, but you'll get more finer rotations, okay, of your rotor. So very often, the least rotation, the specification of motor is, stepper motor is, what is the minimum degree of rotation that is possible. So it is usually 1.8 degree or 0.9 degree. These are the two variants with which you get a stepper motor. Okay. So the, again, it depends upon your application, right? So if you require a deviation in steps of say 10 degree, 20 degree, okay, you can definitely achieve with better accuracy with this kind of arrangement. But yeah, if you require a rotation at lower accuracy, like say if you want uh, rotation of your motion should be there in steps of say zero point 0.1 degree, those will be a little bit more difficult with the stepper motor. So that is the drawback of a stepper motor. Stepper motor can not give a finest control, okay, of your output, okay, and that will be limited by the basically number of poles available on your rotor. There is certain drives called as a wave drives, which achieves the, okay, very small rotations as a 0.001 degrees, but still there is always a compromise that, okay, you'll never get below a particular least count for the stepper motor for position control. But it is again very much predictable and very robust. So torque of these motors are high, and robust control of your output is possible. So very often in the scenario like a linear actuators like this, okay, you'll find stepper motors are, okay, used very commonly. Okay, so the problem which we have seen, okay, that the stepper motors cannot go below certain degree of accuracy. To solve this, there is another type of motor called as a servo motor. Okay, so servo motor is a third type of motor. Let me see quickly. Any questions till now? Okay. Yeah, so we talked about a DC motor. The problem of DC motor was the position control was not fine enough, was not possible. So we switched to the stepper motor. Stepper motor gave us position control, but it does not give us a very fine position control. For that, now we go for a closed loop, okay, feedback. So basically, servo are not the motors. Servo is a mechanism. Servo itself, very, okay, loosely we call this as a servo motor. But servo motor, there is nothing called as a servo motor. Servo is a mechanism with which a motor is controlled. So at the heart, this is the servo motor. But if you look at the exploded view, at the heart of the servo motor, we'll find there will be a DC motor itself. Okay. So in case of a servo motor, there is a notion of a feedback. Okay, so what we have is this DC motor is coupled to the shaft, okay, via the gearbox, and the current position of your, okay, shaft can be found out with the help of a sensor. Okay. So sensor is usually a position sensor is usually a potentiometer, which is a rotary resistive sensor. Okay. So by changing the rotation of this particular potentiometer, the resistance changes, and that resistance is directly proportional to the current position. So by measuring that resistance or the voltage across this potentiometer, we'll come to know what is the current position of the shaft. Yeah. So how the servo mechanism works is it has a DC motor. To this DC motor or to the servo motor, we give a command that is go to 90 degree. So there is a controller, okay, a servo controller. What it does, this controller first senses what is the current position. If current position is 0 degree, then it, okay, rotates this particular DC motor, okay, appropriately so that it reaches to this, okay, desired position or a 90-degree position. If it is already at 90 degree, okay, then it is not going to move it. Yeah? So this is called as a feedback control position. So unless and until you reach to the desired position, the motor will keep rotating in particular direction. Okay. And as soon as a desired position is reached, the servo mechanism is going to stop the rotation of the motor. So this is the block diagram of the basically a servo motor. Yeah. So servo motor, you will find there will be a potentiometer. There is actual DC motor. So sometimes this motor can be in a, okay, industrial system. This actual prime mover or basic motor can be a AC motor also. Okay, but for the sake of simplicity, I kept it as a DC motor. It might be coupled with the gearbox to increase the output torque. The actual position of the shaft will be sensed via potentiometer, and that sensed value will be then compared with the commanded value. So in case of a servo motor, this okay, position of the servo motor is given again with the help of the PWM mechanism, right? So how to tell whether your motor is to be, okay, rotated towards 0 degree or 90 degree? This is done by providing a mapping between a PWM value, okay, and a required output. Yeah. So servo motors, again, these are the standard. In case of a servo, they have decided, this is again an industry standard, that 1 millisecond pulse width and the time period has to be 20 milliseconds. Okay. The entire time period is 20 milliseconds, and T on time is, if it is 1 millisecond, then your command is for say 90 degree or minus 90 degree. It is a relative position. 1.5 millisecond pulse width correspond to a 0 degree position, and okay, the plus 90 degree position is corresponding to 2 milliseconds. So if I change my pulse width, okay, from basically 1 millisecond to 1.22 millisecond, your servo will move from minus 90 to plus 90. Yeah? So if you have smooth control from 1 milli to 2 milli, so this depends upon now your controller. Okay, more smoother control will achieve a higher degree of accuracy. So you can get steps as small as say some micro degrees by changing this particular pulse width to in steps of a microseconds or a nanoseconds like that. So the point I'm trying to make is servo output angle can be controlled more accurately than the stepper, and that basically depends upon your control. How finer PWM can be generated. So finer is the PWM, to get more smoother action, right? So those kind of motors are very often used in you might have seen this kind of humanoid robots or the robotic arms, or these are again fancy robots, multi-cord. These are six hexapods, right? Six-legged robot and all. So where you don't have to move, the motion is restricted, right? Very often these servo motors come into 0 to 180 degree rotation or 0 to 270, uh, and they cannot be moved beyond that particular position. So in case of a servo motor, the position is controlled via the PWM signal. Okay, and again, in case of Arduino, we can simulate that. Yeah, so PWM signal, you can see here. I'm changing the pulse width. I hope you can see this yellow signal. By changing the pulse width, we are changing the position of the servo motor. Yeah, from 0 to 180 degree and back to 0 degree. Yeah. So that is the position control of a servo motor. Servo motor basically has 3 pins. It has a supply pin, a ground pin, and here the center pin is the PWM pin. So PWM pin is the mechanism by which we are telling which position your motor should move. Okay. So here I am creating the pulse width, which is making this motor rotate in steps of about 5 degrees. Okay. So again, control the program for the servo motor is almost similar. Here, I'm using a kind of analog right operation where your output position can be changed from 0 to 180 degree. Okay. So again, for loop is there where we are connecting the servo motor to certain PWM pin. Pin number 3 is the servo pin, and the position is changed from 0 to 180 in steps of 1 degree. Okay. So again, quite easier to control the position in this case. So maybe we will go to the last. Yeah, let me see any questions till now. I think we have some, almost we are reached to the end. Can I borrow some time, ma'am? Maybe 10 more minutes?
Yes, sir. Yes, sir.
Maybe we can look at the last motor and then we can start. Yeah. Let us go to the last part. Yeah, so last motor is the BLDC or brushless DC motor. Again, very often we will be using these motors. You might have seen these motors in the quadcopters, right? So wherever there is very high speed requirement is there, for that this brushless motors are designed. So the brush is the mechanism which is available inside most of the motors, which is connected to your rotor. Okay, so your in case of a DC motor, okay, brushes, in a very simple term, brush is over here. Yeah. So we have seen that this particular device, right? So these two ends, okay, where your coil is nothing but rotor, right? Rotor is in contact with this small loops here, right? So these loops is the way to provide the electrical signal to your coil, right? And in very simplistic case, these are nothing but the brushes. Brushes is the mechanism through which the electrical power is connected to a rotating element. Yeah, and because of this, rotating element is continuously in contact with this particular loop, there will be always a wear and tear. Okay? So brushes eventually after certain time, after say 5 months, 10 months, you'll find the motors will start okay uh, 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 not performing as expected, or sometimes they will not turn on itself because this particular contact itself will get worn out. Yeah, so there is always a maintenance required for a DC kind of motor. And if you can imagine, if I want very high speed motion, this coil might be rotating at say 10,000, 20,000 RPM, and this wear and tear will happen at very often, right? So to achieve or to reduce this, what this fourth motor have a design or came into a picture, that is a BLDC or a brushless DC motor. In BLDC, this entire brush concept have been removed. The motor itself have been revamped. Entire motor construction have been revamped. Usually in the motor, the outer housing of the motor is stationary. Okay, in most of the DC motor, stepper motor, the outer housing is stationary and the central part is what is moving. But in case of a BLDC, the first change or first major change is in the construction that the outer body of the motor rotates and the central core, okay, is stationary. That is the first change. So if you look at this animation, I hope you can see the actual outer body over here is rotating. The central part is stationary in the BLDC, and it is constructed such that the position of this particular outer body can be sensed. This is done with the help of a position sensor called as the Hall effect sensor. And by knowing this particular position of the body, so there are again permanent magnets. You can see those black colored, dark black colored portions. They are the permanent magnets, and the position of these magnets can be sensed by the Hall effect sensors. Hall effect are the magnetic sensors, and based upon their position, the internal coil, there are currently 6 coils. These coils can be actuated, okay, and these coils can be now powered, okay, directly from a battery source without a need of any brush. Huh? So the beauty of this construction is the entire circuit, entire mechanical construction have been revamped, and all the electronic control goes on the central element, which is usually called as a rotor. But in this case, your outer structure is what is rotating. And this gives us a more reliable speed, or this makes it enables this particular motor to rotate at very high speed. Okay. And basically, the control of this motor is done with the help of now a more sophisticated controllers called as the electronic speed controllers, or ESCs. And this ESCs can be connected, can be controlled with the help of the PWM. Again, this PWM came back into the picture. So what servo motors, the PWMs are used. PWM signal is used to control the position of the motor. On other hand, in case of a BLDC, same PWM standard is there. Okay, from Arduino, you need to generate a PWM signal of a pulse width from 1 millisecond to 2 millisecond. But now this pulse width will corresponding to the RPM of the motor. Okay. So the least pulse width will be a minimum RPM, usually 0, and the highest pulse width will correspond to the maximum RPM. Say if it is rated for 20,000 RPM, then by changing the pulse width from 1 millisecond to 2 millisecond, our motor can be rotated till a 0 to 20,000 RPM. So that is again quite often used in the mechanisms where very high speed rotations are required. So in nutshell, okay, if I look at our first section from where we have started, right? So basically, there are, summarize everything now. There are four motors which we have seen today: DC, stepper, servo, and brushless, right? A DC motor, speed control is done with the PWM. Direction is by swapping the terminals. Stepper motor, speed control is done by, okay, reducing or increasing the interstep delays, and direction control is by changing the sequence, yeah, the stepping sequence. Servo motor, okay, the speed is constant. Okay, there is servo motors usually there is no control over the, there will be a fixed speed, for example, a 60 RPM. But the importance over there is the position. Servo motors main use is in the position uh, control. So their position is controlled with the help of the PWM. And in case of a BLDC, speed will be controlled by PWM, and usually direction can be managed by swapping the phases, yeah, or the wires. So that is the overall case summary of today's session. Yeah, maybe, yeah, we can. Yeah, so that's it for my talk. I hope you have understood at least some basic concept over here. Maybe if you have any doubts and queries, you can definitely contact me. Okay, my email ID is
Okay, attendees. So if you have any doubts, they can raise their hands and we will unmute them to talk.
yeah,
Yogesh sir also comes to DBIT every Wednesday, correct, right?
yeah, very
Yogesh?
yeah, Wednesday and Friday, one of them very often. Yeah, next semester I don't know. It depends upon the timetable, right?
Yes, true. But then sir is all students. Sir is all is there
Yeah,
in the campus certain days. You can note down his email ID. He's very gracious to give his email ID, and out of his busy time, he spares some time for DBIT. So if there are any questions, you can raise your hand so that we can unmute you and you can then ask sir directly if there are any questions. Any questions, Prem, in your chat box?
There is some questions I can see. What will be the result if we increase the number of poles in a stepper motor? Yeah, so again, a good question. Uh, this is going to definitely do two things. If I increase the number of poles, uh, one thing is you can get more finer position control. And second thing is by energizing multiple poles at the same time, you can increase the torque of the motors. You can imagine that, let us say, if single pole is energized, your rotor is going to be deflected with certain force. But if I'm able to provide two poles, energize two poles, the force with which rotor is going to rotate will be doubled. So more the poles are engaged while rotating the rotor, higher torque can be generated. So two advantages of increasing poles: a torque can be increased, and definitely the position control is also better. Yeah, so again, good question. I see that was it. That's it.
No more questions, right? Rutvik, confirm, and Prem, we can go ahead with the next part.
No questions, sir.
Okay, then thank you very much, okay, for joining this session. I'll be happy to answer any questions later on. Okay, they can come through your team.
One moment, Yogesh.
Okay.
Rutvik,
Yes, sir. We will move to our vote of thanks.
Oh,
So, dear honorable speaker and participants, on behalf of the organizing committee, I'd like to thank you for attending and participating in the Motors in Automation event. Thanks to your significant insights and active participation, this event has been enlightening and useful. We are very grateful to our speaker who shared the knowledge and expertise on motors in automation and provided useful thoughts into the field most recent advancement and trends. Also demonstrated with the help of simulation, making it more effective and interactive. These talks were instructive, interesting, and motivating, and they helped us comprehend the crucial part role that motor plays in industrial automation. We'd also like to thank all of our attendees for their active involvement and smart questions that made the session interactive. And we hope you found it interesting, engaging, and pleasant. Thank you once more for your participation and efforts to the event. We hope you will continue to interact with us and with one another as we seek to develop the field of industrial automation. Now, I would like you to turn on your cameras because we are going to take a picture with our guest speaker.
requesting all participants to please switch on your cameras.